Okay, let's look at three-dimensional VSEPR shapes for molecules with 6 things around the central atom. Molecules like these here. As we've said, these 6 things can be combinations of bonds and lone electron pairs. We can have 6 bonds, like this one. We can have 5 bonds and 1 lone electron pair, or we can have 4 bonds and 2 lone electron pairs. For whatever reason, in these type of molecules, we don't tend to see more than 2 lone electron pairs. So there are really actually only 3 types of molecules that we'll have to learn the three-dimensional shapes for. Okay, let's get started. We'll start with SF6. So SF6 has 1 sulfur surrounded by 6 fluorine atoms. And this is what it would look like in 3 dimensions. Now, if you remember, we've said earlier that bonds have electrons in them. And we've also said that electrons, since they're negatively charged, like to repel against each other. So the electrons in this bond, for example, want to be as far away as they can be from the electrons in this bond and from the electrons in this bond. We got all these bonds that are trying to push away from each other. So it turns out that when you've got 6 bonds that all have electrons, this is the structure that they take so that they can all be as far away from each other as possible. One way to think about this molecule is that it has a top atom and a bottom atom, and then it has 4 atoms around its middle. But the thing is, any way you turn this molecule, it's kind of symmetrical. So it doesn't really have a top or have a bottom or whatever. But the structure is 1, 2, 3, 4, 5, 6 around the middle. And we call this an octahedral molecule. Let's look at some bond angles in the octahedral molecule. The octahedral molecule, since it's kind of a complex 3-dimensional shape, can be difficult to draw in 2D. But when I draw it like this, I'm trying to show it kind of like this. Yeah, that's not bad. You can see how the model looks a lot like the diagram here. Okay, so anyway, bond angles in the octahedral are actually really simple, because between any 2 bonds you can find, there's always they're always 90 degrees. So every single bond is a 90-degree right angle. So for example, the bond from here to here, which would be this one in the diagram, is 90 degrees. Or the bond from this to this one, these 2 here, that would be 90 degrees. Or the bonds, this is sort of difficult to show, but there we go, between these 2, right there, would also be 90 degrees. So all the bonds have angles of 90 degrees, and octahedral is the way that you arrange 6 atoms around a central atom so that the bonds are all as far away from each other as they can be. All right. Now, we'll keep going and looking at the other VSEPR structures, but I'm going to keep this octahedral up here because all of the other structures are going to be based on the octahedral, so we want to keep it up here as a reference. So IF5. This has 1 central atom surrounded by 5 atoms, and then it has 1 lone electron pair. IF5 is going to look like this in 3 dimensions. Okay? Here are the 5 atoms, and then here is a lone electron pair. Take a look at how IF5 looks similar to the octahedral. If you look at it sort of straight on, they look very similar. But the one thing that's different is one of the atoms up here has been replaced by an unshared electron pair. Okay, so that's the difference between these 2 molecules. The shape of this guy, IF5, is called square pyramidal. And I think that's because if you kind of put it on its side, you can see that in 3 dimensions, it sort of is the shape of a pyramid. So the square pyramidal is like the octahedral, where one of the atoms has been replaced by an unshared electron pair. Okay, angles in the square pyramidal. Well, in the octahedral, remember that all of the bonds were 90 degrees apart. With the square pyramidal, the unshared electron pair up here is pushing down on all of these atoms a little bit more than another bond or another atom would be if it were up here. Okay? So in the square pyramidal, all of these atoms are bent down a little bit. This can be hard to show. So here is an exaggerated model that I made, okay? Here the atoms are bent down too much, but I wanted to show you what I meant by this. You see how all of these atoms are bent down? That's because these electron pairs, this electron pair here, needs a little bit more room. It tries to push everybody a little out of the way a little bit more, okay? So it bends them down, and that means that this angle, the angle here, is going to be a little less than 90 degrees. So this is the angle here that I'm talking about, the angle between this and all of these bonds here is going to be less than 90 degrees. Now it can vary from molecule to molecule, but it's about 81, 82, 83 if you need to know an exact angle number. But the point is it's less than 90 degrees because this lone electron pair is pushing all of these atoms down away from it, making their angle less than 90. Okay. Now finally, we'll look at the last structure here, and that is xenon surrounded by 4 atoms, 4 fluorines, and 2 unshared electron pairs. And here is what this molecule looks like. I always think it looks like a flying saucer or a drone or something. I don't know. So what we've got is we've got these 4 atoms around the middle, and then we've got a lone electron pair on the top and a lone electron pair on the bottom. So this looks just like the octahedral. You can see it looks like the middle of the octahedral. It's just we've taken the top atom and the bottom of the octahedral and we have replaced those both with lone electron pairs on the top and on the bottom. Okay, and so it has this flat shape, and so we call it square planar. Obviously it's square, and planar means that they're all in a plane, and you can see that all of these atoms, the 5 atoms, are all in a nice neat plane here. So we call this square planar, and in a square planar molecule can be drawn like this. Okay, sort of trying to get this view here. And when we're talking bond angles, I could draw them here, but I think it's actually easier to talk about a square planar molecule with a top view because it's just so simple. And all of these 4 bonds are 90-degree right angles. Okay, so here's just a quick wrap up of the shapes. Here's the octahedral shape. This is what we get if there's a central atom that's surrounded by 6 other atoms. If we have a molecule where we have 5 atoms and 1 lone electron pair around a central atom, we get the square pyramidal, where one of these atoms from the octahedral has been replaced by an unshared electron pair. So it has this shape, sort of like a square pyramid. And then finally, if we have a central atom surrounded by 2 lone pairs and 4 atoms, we get this square planar shape, which is just what we'd have if we have an octahedral where the top and the bottom atoms have both been replaced by unshared electron pairs, and then we only have the 4 atoms in the center. So these are the 3 shapes that you have to keep in mind when you're looking at VSEPR for molecules where a central atom is surrounded by 6 things.